How was the test, Matt? A very free test. Did they have any interesting questions?
It's a standardized test. I don't know what you're expecting.
I wish every standardized test they just put like one question at the end, like just put that 100 right out of reach. I mean, standardized tests are already really messed up for a number of other reasons, but like they just had
You
like
can mess
one
them up a
question.
little more.
Yeah. If you maybe if we made them better in other ways. Um,
But yeah, no, it's a very easy, like extremely easy five. The standards are absurdly low.
yeah. Um, well, then this class should be more interesting. We're gonna talk about some good stuff. Were you able to catch any of the mistakes that I made in the video?
Uh, no, not really. You made mistakes.
Uh, there's one offhand comment that I made about a name that I went back and looked at the history of, and
Oh, that yeah. I started with CH.
yeah, the Cholesky decomposition.
Right.
And then there was another one where I accidentally wrote a K instead of a J,
I see.
or an I right here,
Yeah, yeah. That makes that. Yeah, that recurrence. Yeah. Okay.
for the Vandermonde convolution.
Right. So obviously I didn't do it rigorously, but I was able to, I want to say guess, because I didn't do it numerically, obviously, but I was able to guess why the determinants of your triangular matrices were one, or like why you use those.
All right, what's your guess?
Well, it was just kind of a like so it's essentially the same as your water pipes thing. Uh it was just a sum of the components, which can be written as the sum of previous components and the sum of more and more components, essentially.
Yeah, so the the proof um that I gave for the P matrix is almost like word for word the same proof that you would give for the L and the U matrix. You just have to be a little bit clever about where you place the endpoints, but it's literally the same proof three times in a row, which is why I only did it once.
Yeah. Yeah, but is there any algebraic solution to this?
Well, so there's the third proof would be if you took this matrix and you row reduced it, there is a another counting interpretation of the row reduction that you would do that involves taking this grid and omitting certain arrows from being able to be traversed on. And so the all the cases of omitting certain arrows or subsets of arrows corresponds to the actions that you would take when you row reduce it. So
Oh.
it would be more this is like the most algebraic that you can get though. The place where the algebra fails is when you want to take it to an infinite dimensional matrix, and then um the biggest thing that I would be confused about for defining an infinite dimensional matrix would be or sorry, rather the determinant of it at least. The determinant of an infinite dimensional matrix would be this expression right here, where you're taking the sum over all of the permutations of the elements. There's a proving that that infinite sum of infinite products converges would be
I see.
impressive.
Okay.
But people have done it, and the everything that we did is like 90% of the work that you need to do it in this particular case. So,
All right.
um,
Yeah, thanks for solving it. That good video.
well, I before you sent me the email, I actually saw there's this really great professor on Twitter named um Walt. I'll look up his tag when we get off. I forget his name, but he posts like really good like one image explanations of things in linear algebra and quantum mechanics and stuff. And this was one of the things he posted like 3 or 4 days before. And then
Yeah.
actually, like a couple days after you sent me the question, I didn't even know this at the time, but there's a Fields medalist winner named Timothy Gowers, I think. And he started making YouTube videos where he just takes contest problems and he solves them from like this is the first time he's looked at it to so he just like videotapes his process. And he also solved this problem. I haven't seen that video, but as soon as I showed this to a friend, they were like, "Did you just copy Timothy Goer's problem?" Uh, where did you get this problem?
Uh, I found it probably not the origin, but someone posted it on a subreddit that I'm on.
Mm. Yeah, I think the first reference that you could probably find to it in literature, besides the subreddit, would this paper by Gilbert Strang and Alan Edelman is probably a big popularizer of it. Um, and Gilbert Strang is a legendary pedagogue. He's written one of the best linear algebra and partial differential equations textbooks out there. So on that note, we had these four lemmas about determinants and this definition. And this is all really technical stuff. Like right here, when I put the symbol summing over all sigma and Sn, there's tons of group theory happening right here. So how do we understand this? This thing right here too, that the determinants are multiplicative. We saw an example of that when we were looking at a group of 2x2 matrices whose determinants were all plus or minus 1. But it's true in general. And one of the ugliest and least instructive proofs is just to induct on the dimension. That doesn't really tell you anything. So we want to give a good proof, geometric picture where we don't have to think about like coordinates or subtleties about dimensions and how this complicated formula interacts with itself as you go up. But in order to also motivate why we want to study determinants so much and keep it in the context of the calculus that we've been doing, I want to prove these four lemmas. And I want to show us another example of an integral we solved where there was a determinant that I just sort of hand waved over. So will really motivate the connection between determinants and calculus and the things that I'm going to show you today. And then also to keep it connected to the calculus that we've been studying. These L and U matrices are extremely, extremely powerful in the theory of Taylor series. And they suggest a lot of very algebraic interpretations are possible that don't involve traditional analytic ones. So we'll be exploring that a little. What I would like to end at, we might be able to do more than 3 hours worth of this stuff if I'm being honest. But what I want to end at is give an algebraic understanding of why Taylor series are the way they are, give an analytic one. So the really good one, if you for some reason decide to become an engineer, you can have a very good trust in your approximations. And then I also want to give an algebraic proof using the things we're going to talk about today, that integral formulas for polynomials are the way that they are. Because once you have the formula for polynomials, you can use linearity to extend it to series, and then from series to rational functions and all that stuff. So that's just my idea for how we're going to end this, I guess. Because the trig identities are kind of cool, but we can go back to drawing lines on triangles, I guess. But now that you've
Wait, did the 30 minutes leave you enough time for your extra content?
Honestly, I could probably talk for 2.5 hours today if I really wanted to, but except my voice. But yeah, I had a bunch of stuff planned, and I was just planning on going until some of us tapped out, I guess.
Oh no, but like, is an hour and 30 minutes like enough time for at least some of the stuff, the extra stuff you're doing?
We are going to prove these lemmas and then some down here. And we're also going to first, before we prove these lemmas, I'm going to show us where that determinant was that I skipped over. So let's do that now, I guess.
Okay.
I'll go to the top. For some reason, all of my things got rearranged. That's not what we want. All right, so we just make a new page. All right, so wedges. All right. So when we do you guys remember the first way we evaluated this particular integral? Here, let me write it down. Come on, tablet, turn on. There we go. Um, this is a pretty important integral to be able to evaluate because we saw that once we had a scalar value for this, we could use differentiation under the integral to kind of naturally get at, like stumble onto the gamma function. And we also needed this integral to be able to compute gamma of 1/2. So do you guys remember the first way we integrated it?
I do not.
Okay, so let's call this integral I. Then if we multiply this integral by itself, but this time we use the variable y instead, then we can do a bunch of hand waving about continuity and rewrite it this way. And so this thing is equal to I squared, right? So this is where the integral, or sorry, the determinant happened. I said, okay, let's convert to polar coordinates. And I said that this integral I squared that we had was actually equal to this integral. dr and d theta. And the reason that I wanted to do that is now we have this r here and we can perform a u substitution. And this is kind of the original trick in history of how to solve this integral. And this is probably the trick that you will see in any like introductory class after they taught you how to convert to polar coordinates. Because the most hand-wavy thing I did is insert this r right here. And this is where our determinant is, even if it's not immediately obvious. So if you're interested in verifying that this in fact does give you that the original integral was square root of pi over 2, you're gonna want to, it's a good exercise to follow through with this calculation again. But how do we do this change of coordinates? So a u substitution is basically a one-dimensional change of coordinates. Oh. And so we're going to do a little bit of hand waving here. I'm just showing you where the determinant's coming from, and it's going to motivate the particular way that I'm going to prove the 4 lemmas, because what I'm going to show you has a lot to do with integration, even though it doesn't seem like it at all to begin with. So if we have, just to remind ourselves in polar coordinates, we have that x is equal to r cosine theta and y is equal to r sine theta. So whenever we did a u substitution, so I'm just going to compare them here, we would say that x is equal to u of x, and then so dx is equal to u primed of x du. Did I write that correctly? Dx, I should say. Here, wait. So then we would take, no, that's not what we would say. We would say that f of x is equal to u. There we go. So then f primed of x dx is equal to du. So that's what we would say. So the problem is if we have multiple differentials on the outside, I'm using the word differential here very loosely because I suspect that your calculus class hasn't properly justified why we can think of this as an infinitesimal object. And when we get better at Taylor series, we'll see that there might be a reason why we wouldn't think of it that way. And when I did this integral, are these being multiplied together, or are we thinking of them as happening like sequentially in parentheses? So there's a lot of hand waving here is what I'm saying. But when we have two of them together right here, how do we perform a change of coordinates? And so how do we perform this change of coordinates? How does it affect what our differentials look like that we're using to integrate? So I'm going to just rewrite this equation right here, and this is going to be how we're going to generalize to higher dimensional integrals. So I'm going to rewrite f prime of x as the determinant of this single 1 by 1 matrix, f prime of x dx equals du. Why would I do this? Well, let's think about 2D. So if we have a plane like this, and we have some matrix A, B, C, D, we can sort of think of the plane as, if we just think about the integer coordinates, we can sort of think of it as being this very regular, like crystal lattice thing. We're going to come back to this idea later on today. Right now, I'm just drawing pictures to try to help you see what it has to do with integration. So we can think of the plane like this. I am going to be a little nitpicky about this drawing, but how do we interpret the determinant of this matrix? In order to answer that question, we kind of have to understand what the matrix does to these integer points. If we do that, then it's going to be very clear what the determinant is, and we're going to prove this geometric picture as well. I do think I'm going to give you a pretty good, like not standard, not something you would see on a standardized test about determinants in linear algebra, but you'll still be able to solve problems with it. That's my hope. So let's say, for instance, we have this particular matrix 1, 1, 1, 2, something like that. So what we can imagine what this matrix does is it takes this arrow right here, it takes that arrow, and it sends the x arrow to the point 1, 1, and it sends the y arrow to the point 1, 2. So that's going to be that one, right? And so if we look at all the sums of these, it sort of transforms our grid into something a lot more smushed. Maybe I should zoom in for this picture a little bit because I chose an unfortunate matrix to work with. Let's see. So then it goes up like this, up like this, up like this, so on, up. So I'm going to zoom in a little bit. So what we can imagine this matrix did is it smushed the plane. So be looking like this, but or at least this is what the first quadrant ends up looking like. So then we have another one of these going here, and then we have another one going up. That's what the first quadrant ends up looking like. Maybe I'll add some of the other quadrants below. That should be going down there, and this here, this here, this here, that there, that there. So our grid actually still ends up passing through all of the same points, which is actually telling us something else about what the determinant is measuring. Since the determinant of this matrix that I chose, 1, 1, 1, 2, you can check that its determinant is 1. And the determinant being 1 means that this matrix keeps all of, it doesn't like exclude any grid points when it does this smush. Maybe if the determinant like stretched out areas, then this smush would be, then some grid points would be missed basically. But that's not what's happening with this matrix. And so the determinant is already telling us a lot of information that way. But so an integral is about measuring areas. And when we do a change of coordinates, we're changing what we're defining our unit area to be, what was determined by this thing right here, this pink square, maybe that's hard to see against the red that I'm about to draw, became this red square. They have the same area for this particular transformation. Oh yeah, that's super hard to see. Here, let's zoom in a little more. Maybe I can outline it. You won't let me zoom in anymore? All right, here we go. So it became this new area. So when we perform a change of coordinates, we need to account for how our reparameterization of the plane stretches or shrinks areas. So there's going to be a determinant involved in there. So if I wanted to perform this change of coordinates here, what I need to do is, so I have integral fx comma y dx dy, and then I have x is actually now equal to a function of r and theta, and y is equal to a function of r and theta. And so when I do a change to polar coordinates, we're going to have f of x r theta comma y r theta. Oh, maybe I should write this below. Let's write this below. Then I'll have full space. We can make it stand out. There's a lot of hand waving going on here, but we're going to develop the techniques to make this a lot more rigorous. So we have our integral. So f of x comma y dx dy. Then we said x is equal to r cosine theta. Y is equal to r sine theta. And so in order to convert this to polar coordinates, we need to take the function r cosine theta, r sine theta. And then now we need to multiply it by the stretch factor that the change of coordinates have. So that's going to be the determinant of dr of our x, and then d theta of our x, and then dr of our y, and d theta of our y, and then times our new differentials, dr d theta. So before I move on, before we do any computations involving polar coordinates, I just want to gauge where you're at on like how we got this change of coordinates formula.
It's good because this is just the straight definition. It's just pulling a matrix from the square.
Okay.
Or from the
yeah.
previous area, I guess. Not square necessarily.
Okay, good. The first time I saw this, it kind of came out of nowhere for me. But I'm hoping that I'm motivating it correctly. So let's actually do this computation for our integral in question, 0 to infinity. Oh, we also have to worry about the bounds of our change of coordinates, but it's not too hard. It's basically the same thing as what you do with u substitution. So dx dy is equal to, in our new bounds, 0 to pi over 2, 0 to infinity. It's going to be e to the minus r squared. And then we have the determinant of, so the r derivative of our x function is just going to be cosine of theta. And the theta derivative of our x function is going to be minus r sine theta. And the r derivative of our y function is going to be sine theta. And the theta derivative of our y function is going to be r cosine theta. D theta dr. So can someone compute that determinant for me?
R.
Yep, that's just r. d theta dr. And now we are in u substitution land, and we're pretty happy. We can just evaluate this thing from the inside out. Great. So this is our like calculus motivation for why we should care at all about these determinants. Basically, whenever you want to do a change of coordinates, you're going to be taking a determinant. And actually, in a lot of this is in your first calculus 3 class, you're going to learn how to integrate over very funky blobs in 3D space. But oftentimes, it would be a lot easier if you just performed a change of coordinates and then integrated over some very easy space to integrate, which is what happens a lot in practice. So, this is just something to look out for. But in order to properly talk about integrals, determinants, what is their connection to integrals? What is their connection to systems of linear equations? All that stuff, we need to go back to the very beginning. So we're going to model a space as lists of, let's say, n numbers, right? So that's n-dimensional space for us. You can doubt the accuracy of this model, especially given in the fact that we live in a curved reality. But we're just studying a model here. We're studying the geometry of this particular model. So we're going to define, actually, so where I'm going to be moving forward from this, starting at the beginning, I'm going to be mostly following this book, Linear and Geometric Algebra by Alan McDonald. So let me just plug this book for a second. He has a YouTube channel where he goes through some of the elements of the book, and which is very helpful. It's not a rigorous book at all because Alan McDonald is very much a physicist writing for physicists, people who need to solve problems and aren't very interested in like hard theory. But it's really good for undergraduates because he also has a lot of good problems. There's a lot of good problems in this textbook. And the second book in the series, there's one about calculus. This one's just about linear algebra. Is also extremely good. It's extremely good. So I really recommend this for a college freshman or someone who has taken a calculus 1 class. Yeah. Also, this book is extremely piratable. If you go to this website, b-ok.cc, you can get any textbook, especially his. So literally more than any other book I could recommend to you that would be appropriate for your age, I would recommend this book. It's a very good book. It will help you even if you decide you don't want to do math later in your life, but you still end up taking a job that uses numbers, like literally physicist, chemist. Maybe not if you're a biologist, but if you're doing like statistics and stuff, this will still it'll all be helpful. So anyway, with that said, let's get started. So we have our points as a list of numbers, and so we're going to start by defining a vector to be a difference of points. Okay, so so far this is what we've been doing in our geometry problems. We've done this a ton of times, so I'm gonna go very quickly over the computational aspects of this by actually just summarizing the arithmetic properties that these vectors have. So if we think of all of the possible vectors you could make in a space by just taking a difference of 2 points, then they're going to satisfy some properties called the vector space axioms. All right, these are so important. Alan McDonald put them in his book 3 times. I'm just going to follow his direction on the order that he writes them. Let's see, I want the start of chapter 2. There's also a lot of examples of vector spaces. And vector spaces are probably where you're going to study the most in a college math career. So it's a set of vectors. It objects we're going to call vectors. So maybe I'll just say objects. Let's see. It's a set of numbers plus objects with two operations. And that is vector addition and scalar multiplication. Scalar. Okay, and we're going to call this set, actually, let's call it v to the n. Okay, and it has these properties. So this is the 0th axiom. And so for all vectors in Vn, let's say, do you guys know what these symbols mean?
Yeah, this is just number sets, right? Like there's real.
Okay, so have you seen that notation before? Yeah, the first one's real. Okay, so this is real, rational, complex, mod A prime. Okay, but not something like this. Have you seen this symbol before?
I have not.
Okay, so this is the integers. And this is integers mod a composite. Okay. I'm sorry that I'm busting this out, but I just want to be really specific about what I mean by a number. I mean something that if it's not 0, we can divide by it. So that's pretty important. So let's say A is in one of these number sets, but not these. It can be any of these that you feel like. These are just the numbers that our lists are of. So we could have lists of real numbers, lists of rational numbers, lists of complex numbers, lists of numbers mod a prime. All of that is fair game. So for all numbers, basically, that you're using, and vectors in your vector space, Vn, we have A times V is also in our vector space. So A times V is our operation of scalar multiplication, where you just do multiplication of the number to each of the components. We've done it a ton of times. So then the next axiom that we have is that vector addition is commutative. And we're calling this an axiom because there are things that are not lists of numbers that we would like to think about as vectors. And this is more like a condition that we have to verify holds. But if we're just thinking about lists of numbers, then you can prove this as a consequence of how we do vector addition. So then the second axiom is that it's associative. Again, if we're just thinking about them as lists, then this is really straightforward actually to prove. But it's just good to identify these as conditions we need rather than obvious underlying computational things. So then we have a special vector called the 0 vector, such that if we add it to any vector, we get the thing back. Okay, I'll go back over. Just let me know when you're back. Okay, so the 0 vector, we're just going to think of as a list of all zeros. And in this case, of course, it behaves this way. And then we have this one, which is going to be 1 times V is equal to V. is what we would want from a multiplication. And then this one, we have that scalar multiplication is associative. Two more. So there's 9 in total. We also have a distributive law. For both scalars and vectors. So when we're proving things about vector spaces, it's really good to not reference the inside of the lists, to pick a number n and then write all your vectors as lists and then do everything manually. That can get tedious, and for certain complicated things, you then have to induct on the dimension, and we don't want to do that. So when we talk about coordinate-free pictures, what we're really meaning is we don't think about axes. And we don't think about the inside of vectors, which is their list components. So a coordinate-free picture of a vector is just this. That's it. We're not specifying in what dimension it's living in. We're not specifying which numbers that we're using to do all our operations. We're just thinking about an arrow, and that's what we would really like, because that is more reflective of the geometry of our daily life. And so we should have a model of geometry that doesn't rely on a specific choice of coordinates for like proving theorems. When you're doing actual computations on like a computer for graphics or integrating something for like measuring buoyancy or whatever, then you pick a coordinate system. But when you're proving theorems or formulas, you don't want to look inside. That is generally going to be more work than you need to do if you're thinking intelligently. So all of our vector space axioms have a coordinate-free picture. For instance, the 0th one says that if I take a vector and I stretch it out, I'm just going to get another vector in my space. This one right here, the commutativity of addition, says that it doesn't really matter which order I add my vectors in, we're still going to end up in the same endpoint. And so it's pretty useful to get a coordinate-free idea of all of what these axioms mean. So like associativity means that you can take any route, like if I have this and then this and then this, like on a cube. Let's go back here, see if I can quickly draw a good cube. I could do, let's say 1, 2, 3. I could do 1 and 2 and then 3, or I could do 2 and then 3 and then 1. So the adding a 0 vector says that, you know, if you don't go anywhere, you don't go anywhere. So I'm just gonna make this a fat dot to represent we put a 0 on top of it, but we're still there. This thing says if you don't stretch out a vector, then nothing changes. This thing says you can stretch out your vectors in any order, doesn't matter. This thing says you can add your vectors and then stretch them, or you can stretch them and then add them. This is saying the same thing about stretches, and you know, you could add the stretches beforehand. But we want to have a coordinate-free picture, and we want to prove things that way. So now that we have actually, can you identify a group in these axioms? This is 9 axioms, but with a group we had 4. So can we actually find a group inside a vector space? Let me just remind you what the group axioms are. So we have closure. If we combine any two of our objects, we stay in the set. And we have associativity. And we have an identity element. So we have a 0. And we have inverses. So we actually can't identify a group until we prove a theorem, actually. Let me zoom back in. So these are some good coherence proofs that we can do at the beginning that should all have coordinate-free pictures. So we want to find a group, which is just going to be our vector space under vector addition, but we need inverses. Okay, so in a coordinate-free picture, we would just have, all right, if this is my vector v, then v inverse should just be, or minus v should just be the vector pointing in the opposite direction. And this is pretty good, actually, because if we think of this as point A and point B, then v equaling to b minus a is extremely consistent with saying minus v is equal to a minus b. So that's a good coordinate-free picture, but let's prove it using our axioms that we have so far. We want our proofs to be coordinate-free. We don't want to use coordinate-free reasoning as our proofs, if that makes sense. Maybe I can state that more precisely, but you'll see what I mean as we go on. So we want to prove this. Number one, that v plus -1 times v is equal to 0. So as soon as we can prove this, then we found our inverses. So I would actually recommend that you write down these vector space axioms because I want to reference them at each step of our proof. And once you know how to look for a vector space, probably going to find a lot of them. Probably going to find vector spaces all over the place.
All right, I've screenshotted.
Okay, so let's just start with this equation and see. We'll start with the left side. So v plus -1 times v. And I'm going to stop writing the arrows when it's clear that I'm talking about a vector or a scalar. In a textbook, they usually talk about vectors with a boldface. But I can't really write in boldface on this very efficiently. So what axiom can we use on this thing? Or let me write this step and you tell me what axiom I used.
The fifth one.
Okay. Now, what would be a good step to use after this? Oh, that should be a plus sign in the middle. My apologies. We could go ahead.
0th?
The 0th would tell us that that this is still in our vector space and this is still in our vector space, but it's not really a very arithmetical one beyond that. What if we just factored out the v? Then we get 0 times.
So 7.
Yeah. Yeah. All right. So now with this theorem that the additive inverse of a vector is -1 times that vector, great. We have found our group. Vectors form a group under addition. Let's prove a couple more theorems using our axioms. Okay, so if we multiply on the right by 0, we get 0. Ooh, did I say anything about commutativity? About scalars? I guess I didn't. So let me check Alan McDonald's book real quick if I missed something. If not, I'm going to add one more axiom, which is actually a little bit more powerful than the it's more than a vector space axiom. Or let's see. Oh, that's the zero vector. That's the zero vector. Okay, okay. Anything times the zero vector is equal to 0, the zero vector. Okay, this makes way more sense. But actually, I'm just going to throw in this axiom that I'm going to use for every single product I'm ever going to talk about after this is scalars commute with anything. We don't need it. Technically, we can get away with doing everything as left multiplication for the purposes of vector spaces. But this is not a bad thing to assume. Scalars commute with everything. So we'll keep that in mind for later. So how do we prove this one? That any scalar times a zero vector gives us back the zero vector. Well, we definitely have to start with just this side of the equation. Excuse me. A times 0. We could use the first theorem now that we know how to find inverses of vectors. I'm going to use the first theorem. And from now on, I'm just going to write minus v instead, since we know that it exists and is unique. I know I should write that as a -1 right here. -1 times this. There we go. All right. I'm just doing this for precision. So -1 times this times v. Okay. So then I want to distribute our scalar. So we have AV plus A times -1 times V, which I'm going to think of there as being a 1 here. And then I'm going to use associativity and commutativity to rewrite this as AV plus -1 times AV. And I'm just going to call this W. And W. So again, we have 1 W plus -1 W is equal to 0 by theorem 1. Okay, so this is a good proof because we didn't have to look inside the zero vector and see that actually all of its components are 0. So obviously distributing an A is going to be the zero vector still. So this is what I mean by like a coordinate-free proof. So the next theorem, I have it right here, I wrote it down, is, this is a good one. If A times a vector V is equal to the zero vector, then either A equals 0, the number, or V equals 0, the vector. Later on, we're actually going to be thinking of these as the same thing, but not right now. So maybe I shouldn't have even said that. We'll get rid of that. So who thinks they can prove this one?
Uh, can't you just use the first and second theorem?
Something like that. So we got to split it up into cases, right? So case one, I guess the only case that really matters is we can just say, suppose A is not equal to 0. And then, yeah, you get the, well, so suppose, no, actually, this is why I'm insisting that we're able to divide by anything, right? So suppose A does not equal 0. So, but we still have this is equal to 0. And so we want to show this. Remember that we can divide by A. This is really not something you should be overthinking.
So divide by A.
Yep.
Right, forget about that one.
Is equal to 1 over A times this. And then we just use the theorem we just proved. Great. So last one. And that is at, oh, I should put a 4 there. Oh, now it is deciding to lag. It's because, you know, the sun's setting, the sun shining directly in my room, the computer's getting hot. Let's see, additive inverses are unique. Right, so there's only one vector that is the same length but pointing the opposite direction. I haven't said anything about lengths. Keep that in mind that actually the vector space axioms don't tell you anything about length. That's an additional constraint that you apply. So additive inverses are unique. So I'm just going to prove this one by contradiction. For contradiction, assume W1 does not equal W2, but V plus W1 equals 0 equals V plus W2. So we knew before that that if we just add -1 times a vector, that will get us a 0 vector as well. So using commutativity, I can insert this -1 times V into this. What? Gotta put that over here. Great. Oh, it's starting to really lag. All right, -1 times V is equal to V plus -1 times V. Let me move this out of the way. Plus W2. And that cancels and that cancels. So what we're left with, which is our contradiction, is that W1 equals -1 times V equals W2. Then some of my professors write this to mean a contradiction. So yeah, additive inverses are unique. So I'm going to make a definition now after we prove these theorems that are just like coherency theorems that basically tell us that our coordinate-free pictures make sense. Let's make a definition. So if W is a subset of Vn, and W is also, come on, a vector space, is it that my thing needs to be charged? Here, let me see. Fine, this is just getting difficult to write. Can you guess what the definition is going to be? And if W is also vector space, then W is called a subspace of Vn. All right, so this is an important definition because we're going to talk about a certain way to make sets or subsets of vector spaces. Okay, so let's say I have 3D space. I'm just going to draw these arrows here. And I have 2 more arrows like this. And then what I do is I take the set of all combinations of these arrows. So let's call this one actually V1 and this one V2. And I look at let's say W is equal to the set A1V1 plus A2V2, where A1 and A2 are rational numbers, let's say. Okay, so we look at this set. So we have V1, but we also have twice V1. We have 3 times V1. We have 4 times V1. I'll just go stop there. Similarly for V2, but it keeps going even though I stopped writing it. And but we also have V1 plus V2. And we also have V1 plus 2 V2, V1 plus 3 V2. Okay, so I'm just going to draw this picture for a while. But can you tell me anything interesting about this subset of vectors?
It's similar to a matrix.
Similar to a matrix. We're getting this like grid lattice thing appearing by all of these combinations. Let me also draw the minuses going out. So we also have these different quadrants. Does this, I've been drawing a lot of grids recently. In some ways we can think about vector spaces as just being grids. So that's kind of a very leading thing to say when I re-ask this question. What can you say about this subset? Just by looking at it. Well, let's think about it geometrically for a second. This thing's definitely a plane, right?
Yeah.
Is there any planes that you're familiar with that aren't just ambiently existing in some 3D space? Well, like there's the 2D plane, right? Can we say anything special about the 2D plane? Yeah, this is the origin right here. Doesn't this kind of remind you of the 2D plane, just, splayed out in some larger ambient space?
Yeah. I don't know what you're getting at.
This subset is actually a subspace. Right? Because we're saying that this set is all of these combinations that we can make if we were having lists of rational numbers. So let's check that it satisfies our definitions, right? It's closed. We still have commutativity. The commutativity is inherited from above the larger set. The associativity is inherited from above. We have the origin in there because we can just do 0 times V1 plus 0 times V2. This is inherited from above. This is and all of these are inherited from above. So our set W, this is a subspace. And a better name than W is we say this is the span of V1 and V2. Maybe I'll draw this on top. So these are our coordinate axes. But we have this, so we have our 3 coordinate axes out there in space, and then we just have some other plane passing through the origin, just existing there. I'll give you a simpler example. So let's just think of the regular 2D plane. And let's say this is our vector v. Then the span of v is just going to be this line through the origin of all the scalar multiples of our vector. But that's actually a subspace. That's a one-dimensional subspace of our 2D space. So if S is a set of vectors v1 through vk, where all the vi's are in some big vector space, then the span of S is a subspace of Vn. So I want to do like a comprehension check here, just to make sure I haven't lost anyone. Starting from this definition. Okay. All right. I really want you to have pictures like this in your head, though. Focusing on things that happen in 3D is what you want. Span of vectors is a set of what we call linear combinations. Linear combinations. Okay, so let's look at 2 examples of spans. So let's say this is my vector space in 3D. And I take a subset of this vector space, which is just these 2 vectors, v1, v2, are x and y vectors. All right, so, and we're going to imagine this is going to be v3. It's just like coming out of the computer screen, right? And so the span of v1 and v2 is going to be, you know, just the computer screen, basically. I'm just going to draw a 3 by this little 2x2 grid, 3 by 3 points, and so that's equal to the span of v1 and v2. Okay, so what if I throw in this vector right here? All right. It turns out that the span actually doesn't change at all. v1, v2, v1 plus v2. We're not really adding new information to our subspace, right? We've given ourselves a new way of walking. You know, this might be a more efficient route to get from the origin to this corner, but we haven't really made our space bigger at all. Can you think of a vector that I could add to the span of v1 and v2 so that the new span is now a 3D space? What if I added v3? That one right here. This. Suddenly I can take this square, this blue square, and pull it out of the page. So V1, V2, V3. And we have that these two things are equal, but these two things are not equal. So this actually takes us right onto the doorstep of determinants and their first, like, why you care about them, and also what they allow us to tell about these kinds of things. So can you give me a rough reason why adding V1 plus V2 to our span didn't change it, but adding V3 did?
Because you V1, V2, or V1 plus V2 is on the same plane.
It's already in our span, right?
Yeah.
Yeah, but V3 is not in our span. So that's going to give us some new definitions. So we say W is linearly dependent on V1 through VK if W equals A1 V1 plus dot 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 all the way up to AK VK for some AIs, right? And so we get a theorem. It's pretty obvious, and I'm going to let you prove it for that reason, that adding a vector that to a set here, oh, it's still lagging. Oh, okay, there we go. Adding a vector to a set which it is linearly dependent on does not change the span. All right. And so I'm going to take another definition. So if we have a set of vectors v1 through vk, we say it is is linearly dependent. So now we're not thinking about a specific vector and some set of vectors. We're just thinking about just a set of vectors with no one specifically singled out. Is linearly dependent if there is a non-trivial. So I'm going to underline this word because we're going to have to come back to this. If there is a non-trivial solution to A1 V1 plus dot 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 all the way up to AK VK equals 0, where non-trivial means that some AI does not equal 0, basically. Let me show you why this is a good definition. So if I just take a triangle in the plane, I can think of it as being oriented. We only need 2 arrows to really span the whole plane. And as soon as I add the third arrow, so let's say A, B, and C, then we're getting A plus B plus C is equal to 0. This is actually a really important condition for a set of vectors to be a triangle, but we don't need to think about that now. We're going to use it later, but some of these theorems I'm not going to prove, and so this one I said is kind of obvious, so you can prove it yourself. There are some theorems that are not as obvious, which I'm not going to prove, and I will let your professor in your linear algebra class prove for you, because they're not. It's not really that important to go over the details of their proof. So with this definition in mind, we say and we're going to give you all the tools to prove them anyway. So we say a set of vectors v1 through vk is linearly independent if the only solution to a1 v1 plus dot 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 to ak vk equaling 0 is the trivial solution. Where all ai's equal 0. Okay, so what we had before is that the span of v1 to vk is a subspace of vn, and if, which we're calling w, if the set v1 to vk, whoop, let's see if you'll take it away. Okay, there we go. Is linearly, let me state a theorem first. It's easy to prove. It might not be obvious, and I'm giving you all the tools, but it's not that important that we dwell on the proof. So here's a theorem. Decided not to write it. So if this set v1 through vk is linearly independent, then there is only one solution to a1 v1 plus dot 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 plus ak vk is equal to another vector w in our span of the v's. So we're saying that if we have a linearly independent set of vectors and we take another vector in their span, there's exactly one way of writing them this way. So let me return to our 3D example and let's look at it again. So I did press white here. I want it to stand out. Let's try white again. Oh, now it's not writing. All right, thank you, OneNote. Let's try to make this work. So we have these arrows, and we just take this one and this one. And so we had this before, and then we had this pink arrow. I definitely pressed on pink. All right, we had this pink arrow. And so let's call this W. We said W is equal to V1 plus V2. And there's no other way of writing W as a linear combination of V1 and V2. That's a theorem. If they're linearly independent, then there's only one way to do this. It's not that hard to prove, and I'm going to leave it as an exercise for you to prove. So, so that's great. We would like, the best sets of vectors are linearly independent sets of vectors, unless you're talking about triangles, but we're not. If we're just doing pure linear algebra, then linear independence is exactly what you're looking for 99% of the time. So so let's go back to the theorem that I was going to state. Another theorem that we're not going to prove, but it's kind of just like a coherency theorem. If W equals span of V1 dot V2 all the way up to VK, and this set V1 VK is, I'm going to just write L dot I now for linearly independence. Oh, no, this is not a theorem. This is definition, which is a subset of Vn. Well, it's not going to write definition there. Okay. Then we say this set VK is a basis for W. All right. We have covered a ton of ground that would normally be covered in a linear algebra class. And we skipped a bunch of theorems. They're proofs. They're not that bad. I'm giving you all the tools to prove them, but we've covered a lot of ground. So let me know now if you have any problem with my definition of basis, or if you would really like to see a proof of some of these things.
No, I'm going to try and prove these by Monday.
Great. So let's see. Let's do some time accounting real quick so that I know how to like make this flow reasonably. Do you want to stay past 7 to like 7:30, or do you want to just end at 7?
I have to go at 7.
Okay. All right. And then is there any other days this week or this weekend that you would like to do these classes? Because I'm trying to get these done.
I can't do it on Friday or Saturday. I have 2 math competitions.
Ah.
But yeah, Thursday works.
All right, great. That's perfect then. Thursday then. We could probably do like, how long do you want to go on Thursday? Because Thursday afternoon I'm completely free. So we can start at 5, we can start at 6, whatever you guys want.
Is a 2-hour session okay?
Yes.
Okay.
To be honest, I doubt a little bit that we're going to be able to reach my goal of algebraically proving the power rule for integrals if we only had another 2 hours, especially if we wanted to talk about Taylor series. And also you guys have been very patient with me. So how about I entitle you to one more free 2-hour session after that?
That's good with me.
Yeah.
Yeah, I can do Thursday then Sunday, if that's okay with you.
Yeah, I'll have to coordinate a little bit on Sunday because I think I'm doing something at like 4, but after that I should have a few hours free on Sunday as well. And can you do before? I don't see a reason why not, I guess. Yeah, when we're all fresh in the afternoon or in the early afternoon, sure. 1 to 3, 2 to 12. You tell me on Thursday what is best for you. Oh yeah, because the weekend classes are over, right, for the semester. So great. So
after 2:30.
Okay. Let me look at my notes real quick because let's see. We talked about linear independence. We defined what a basis is. All right. So here's a theorem. Any 2 bases, I don't know the plural. So we're gonna have to live with that unless you want to correct me. Any 2 bases have for a vector space. Yeah, so I should write that to avoid ambiguity. Any 2 bases for Vn have the same number of vectors. Vectors which we call the dimension. So this theorem right here is actually one of the #1 reasons why vector spaces are so nice. There are a lot of things that actually do not have something similar to a basis, but like, so for instance, a group can have something called a generating set, but the smallest generating set of a subgroup can be larger than the generating set of the group that it's in. There's no nonsense like that with a vector space. And also we have that as a corollary, if W is a subspace of Vn, then the dimension of W is less than or equal to the dimension of Vn. So dimension vector spaces are very well behaved. All right, so that is the beginning. We have finished the beginning of linear algebra. We have arrived right on the doorstep of why the first reason that we care about determinants. So let's ask a question. How do we compare two distinct bases? So for instance, do they define the same basis? Or do they define the same subspace? Oh, come on. It's not going to tell me. It's not going to let me erase. Come on. Oh, now it's writing. It erased and now it's writing again. All right. Subspace. Let me real quickly come up with two bases that are not immediately obvious that they define the same vector space. It's really easy to come up with examples. So say all right. So I'm going to give you 3 sets of vectors, and you tell me which 2 sets represent the same subspace. This is almost more of a rhetorical question because I just want to elaborate or like help you get a sense for why this might be a difficult problem if you just do it at first glance. All right. So we'll call this set right here W1, W2, W3. So which of these are the same? So 2 of these define the same subspace. Which are they?
1 and 3.
1 and 3. That is correct. And it's pretty nice when you realize that 1 minus 3, 7 is equal to 4 minus 2, 2 minus 3, 1, 5. So I just replaced a vector, the first vector with one that was already linearly dependent on the set. And then 4 minus 2, 2 is equal to 2 times 3, 1, 5 minus 4 minus 2, 2. Oh, I wrote the wrong one. That should be a 10, 0, 8 here. Did I still write it incorrect? Oh, that should be a minus sign. That's a 2. Let me just make sure I wrote this correctly. Minus 3, 10. So then if we did this, that would be a minus sign, and that should be a minus sign, and that should be a minus sign. I guess the minus sign didn't make a difference in this case, maybe. But anyway, just like taking two sets of vectors and then trying to see if each one of uh, the bases is linearly dependent on the rest of all the vectors in the other. That's time consuming. It's not feasible. It's not really feasible by inspection. This isn't an easy problem when you're working with large vector spaces. However, there is one special case in which is really easy, and if we're going to want to try to generalize off of that. So, one-dimensional subspaces. This is what we really want to emulate when we go on to working with determinants. So I said that a determinant is, how much it is stretching the areas. We're going to see that that is a complete theorem. That is a very advanced thing. You could take that as your starting point, but there's a much simpler way to arrive at it in a very natural, like you just investigate obvious things and you arrive at it. So for instance, if I have these vectors, v1 is equal to 1, 2, 3, v2 is equal to -1, 0, 1, and v3 is equal to -2, -4, -6, we could actually, in some sense, say that, v3 is actually just equal to, let me start the sentence over. We could just say that, v3 is a scalar multiple of v1. And whenever we can write an equation like this, it really begs the question, now it's disappearing. Now I can't write. Oh, that's the eraser? Okay. This is great. This is a great learning moment. All right. It really begs the question, can we write this v3 over v1 is equal to -1? I'm going to say the answer is both yes and no. And really getting into the yes and no is like a reward for what we're going to be doing. We're going to be able to conclusively see that yes, we can do this, and also no, we can't do this. So if it's like vectors like this, we can only divide vectors if they're in the same subspace, if they define the same subspace. Then the division is well defined. But if we have two vectors pointing in different subspaces, then we're going to have problems. We're not going to be able to have a simple ratio like this. This 2 got deleted. That should be -2 right there. So the other thing is when we're doing division, we better have a multiplication floating around somewhere. When they're pointing in the same direction, we're piggybacking off of the scalar multiplication. But if we have time, or actually, if you read Alan McDonald's book, you will learn the multiplication that will let you divide any two vectors. I sincerely cannot recommend this book enough. It is a really, really good book. And most linear algebra textbooks will say, oh, no, you can't divide vectors at all. Not in any case. But that's because a lot of linear algebra textbooks haven't changed since the beginning of the 19th century. This is a very modern book. This is a book where you could say to yourself, okay, I just want to do problems to study modern techniques that are efficient and unlock intuitions that will be helpful. Because you can spend a lot of time not doing that. So this Linear and Geometric Algebra by Alan McDonald is the one to read. So how do I want to say this? Is there any more questions that I want to ask to motivate what we're going to do next? Where did my notes go? So many stuff. Okay. Another thing is if we just have a random set of vectors, here's another question. How do we detect linear independence? How do we detect linear independence? Um, so I guess this is the question that I'm just going to leave us on, actually. And so we've set the stage about even getting to the how we why we care about determinants. Where does that definition involving sums of permutations of coordinates come from? All that stuff. There's actually two ways to answer this question, and you're familiar with both of them to some degree. So I'm just going to write wedge product here. I think I've shown you guys the wedge product before, but I never did anything about vector linear algebra and vector spaces. So it's kind of like just using the tool to do geometry rather than really understanding the tool. And then here we have solving systems of linear equations, which I'm sure you guys are great at. But actually, these two things have a lot to do with each other. And we're definitely going to see why the determinant is saying anything about solutions of linear equations. So out of this, we're going to get determinant is 1, and then we're also going to get good answers to our questions. And then, so one thing I forgot to say, I definitely should have said when we were doing the Gaussian integral, is we did our change of coordinates for integrals with something called a Jacobian matrix, or the determinant of the Jacobian, which is like a generalization of U substitution. All right, Jacobian. And really, this falls under the overarching theory of differential forms, which we're really not going to go into because you need to take a Calc 3 class first. But if you go to a good school, they will teach you Calc 3 in the language of differential forms. UNLV is not a good school, just FYI. So we're going to get change of coordinates, differential forms. Once we have the determinant, we had that nice cubic identity we started our class with like a year ago. And a lot more. Let's say, do you guys know Kramer's rule?
I do not.
All right. Oh, that's how long it took to register I was writing. Let's see what Asher said. No, you haven't seen it? I'm surprised. Okay. I'm just gonna write this. It also gives us the shoelace formula. And let me see if I can just remind you of Kramer's rule. So Kramer's rule says that if we have ax plus by equals e and cx plus dy equals f, then that tells us that x is equal to, excuse me, ed minus bf over ad minus bc, and y is equal to af minus be over ad minus bc. I feel like I've talked about this before in the context of determinants. It's not really worth it to memorize this formula for solving a system of linear equations, but Kramer's rule is basically the formula. If you just give us a general system of equations, Kramer's rule will tell you the answer. We're going to get all of that, which is our connection to solving linear systems of equations, out of the wedge product. Once we have the wedge product, as well, actually, we can talk about the Jacobian and differential forms. We're not really going to talk about that anymore, but we can. Here, let me erase this. This is the big one. This is the real magic. It's not going to let me erase it. Number 6. We can get a completely algebraic theory of integrating polynomials. And more complicated regions. with no approximations. Well, you don't need approximations to set up the theory. It will tell you how to make good approximations, though. So that's the part that I would really like to end off with. We're gonna, okay, if we have 4 hours, tomorrow I will do, or on Thursday, I will do the wedge product, probably prove Kramer's rule and the lemmas about determinants, and it'll be easy to see the shoelace formula falling out of it and answering our questions. And then maybe I'll spend the second hour talking about Taylor series and how these matrices that we saw in the Pascal's matrix question are related to Taylor series. They're very related to Taylor series. And maybe then we will spend our final day doing integration of a robust theory that would satisfy any philosopher from the 19th century concerned about a crisis in the foundations of mathematics. I hope this was a cool class. I hope this is better than doing trig identities. You guys are free to go or ask questions or pose any problems to me if you would like.
I've not got any new problems. But I was going to ask, with that site you provided, yes, I have it pulled up, but do you know of any good, like, I guess, intro textbooks that aren't like computer heavy, with graph theory or not and game theory, but with graph theory or game theory books? Because those seem like kind of approachable subjects for someone of my, I guess, math background.
Graph theory is awesome. Actually, this morning I used graph theory to prove something about group theory. But let's see. So I have this book, A First Course in Graph Theory by Gary Chartrand and Ping Zhang. This was the first graph theory book I used. I'll put that in chat. And that was in a class specifically about graph theory. It's a good book full of nice problems, but actually every graph theory book is full of nice problems. But Gary Chartrand and Ping Zhang are actually field experts. So you can do a lot worse than reading their books. And then this book, Introductory Combinatorics by Richard A. Brualdi, was my general purpose combinatorics books that I took at UNLV. I would say the best, I'm going to give you a power ranking of professors at UNLV. There is Dr. Berrigar, who is the geometry professor. He's really good. There is Dr. Robinette, who was my combinatorics professor. She is amazing. In many ways, she's much better than Dr. Berrigar, but Dr. Berrigar was the Canadian Math Olympic coach in like 1998 through 2001 or something. So he has attained GOAT status.
And he teaches at UNLV.
Yes. UNLV maybe 10 or 20 years ago was a very bustling school with a lot of talent, but now they have a lot of really old people who are very comfortable. Also, it was probably never that good of a school. So below, the third in charge is the department chair, Dr. Wu. He's just an all-around really good professor. And then the rest of the professors at UNLV kind of suck. But so my combinatorics professor, she's amazing. She's honestly my favorite professor of all time. And this book, Introductory Combinatorics, here, I'll write this in the chat, is also fantastic.
I pulled them both up on BOK.
Okay. But one thing I wish that Dr. Berrigar, Dr. Robinette, and Dr. Wu all did, which none of them did, is I wish they listened to me about geometric algebra, because it was relevant in every single one of their classes, especially in Dr. Berrigar's, especially in the classes that I've taken with Dr. Berrigar. But this book is so good. This book is so good. I could honestly just talk about the history and success and all this stuff of geometric algebra for hours and hours and hours. But I'm not going to do that. I'll let you go.
All right. Thank you for the book suggestions.
Later, Matt.
Have a good day.
You too.